Okay, so once we're done with this first model, we're now gonna switch from modes within Fusion. We're gonna go from a design perspective into this thing called a simulation. Okay, so essentially what we're gonna try to do is we're gonna simulate different forces acting on this particular component, and we're gonna try to see if the component will actually hold on to those forces and not break and be able to survive, right? So all you have to do is hit design, top left corner, go to simulation, and this different view is going to open up. Okay, now as far as a simulation goes, we have different types of studies, right? So the main or the most basic type of study that you can do is this thing called a static stress. So everything's static, nothing's moving. All you're doing is sort of constraining the component, and you're applying some forces, and you're gonna see if this thing's gonna hold up, right? There's other ones like modal frequencies, electronics cooling, thermal stress, buckling, nonlinear static stress, event simulation, and shape optimization. Okay, so for this class, because this is an introductory level, we haven't really covered any stress really by math on any example in class. So what we're going to do is we're just going to try to apply a static stress type of study, and then we're just going to do a very simple type of study. We're going to see if this thing holds up given the material we select and the constraints we use and loading we use, and then we're going to see if this thing fails or if it holds up the way it should, right? So again, static stress, hit create study, and then it's going to show up something like this. Okay, so what we're going to do is we're going to actually go step by step on the process of actually creating this study, right? There's also this little pre-check type of list that's going to let us know if we have everything set up correctly, where we can actually solve this study. Okay, so first things first, let's select a material for our component. So in this case, we have the single component on our environment, and the material it's selected as default is steel. Okay, we can take a look at the properties. So we can take a look at things like density, Young's modulus, Poisson's ratio, strength, tensile strength, all of these things, right? Now, if you don't want to use steel and you want to use something else, then all you have to do is go to steel. Notice that little pencil open up, and we're going to essentially overwrite the material that we're selecting. Okay, so there's built-in libraries into Fusion. So there's things like aluminum, copper, granite, iron, and then you also have plastics, usually like things you would 3D print and stuff like that, right? So you can select really anything you need, and if there's something in here that you need but it's really not showing up, then I think there's a way for you to sort of create that new material, input all of the characteristics and properties, and then Fusion will automatically take those new properties, do the math that it needs to do, and then show up with the results that you're expecting, right? So again, we're going to select the material. By default, it's steel, so we're going to leave it at steel. If you want to modify that, playing around, you can go ahead and do that. I'm going to select OK. Now, the next thing I'm going to do is, before going to constraints and loads, let's go into this thing called the mesh. Okay, so I'm going to right click, and then I'm going to go into mesh settings. Okay, now the mesh is very important in any type of simulation that you're going to do in the future, because the mesh size actually depicts how far the calculations have to run. So if you have a mesh that's very wide, like you have a lot of space between nodes, then there's not really a lot of calculation that needs to happen, but the accuracy of your results is going to decrease. So it's going to be very fast solving that simulation, but the accuracy might not be 100% there, right? Whereas if you have like super small mesh, so let's do something like a 1%, and then So it's going to automatically give you something like this, right? So it's giving us an error that says if your mesh is very fine, then that probably means that it's going to take a lot of computing power. It's going to take a very long time, and it doesn't quite guarantee good results, right? There's a limit as to how good of an accuracy you can get. We don't suggest you go to like 1%. Maybe stick to something like a 2, 3, 4%, something like that. And then what I can do is I can go to mesh again, right click, and then generate the mesh, and then it's gonna sort of generate the mesh, and hopefully it's gonna show it up. There we go. So here we can see the mesh. This is somewhere close to a 4%. So again, it's pretty good. It's a reasonable size mesh. Let's switch back to a 10. Let's see what that looks like, so you all can understand the difference. And then what I'm going to do is I'm going to generate the mesh again. It's going to generate it, and there we go. So as you can see, there's a lot bigger gaps between the mesh, right? Now for something like this, since we're going to do a very simple type of study, the mesh doesn't have to be like super fine. Something around between 5 to 10% should be good enough for this type of simulation. Okay, the accuracy should still be there, so we should be good. So there's my mesh. We've covered two things so far. We've covered the materials, we've covered the mesh. Now let's go to this thing called constraints. So constraints in simulation are very similar to constraints in modeling, where a constraint is nothing more than a relationship between two components. In this case, it's not two components, it's the one component and the environment that it's going to be subjected to. So in this case, let's try to think of where this thing is going to be placed in real life to try to replicate that simulation of the loading, right? So this is probably going to be placed against the wall, and it's going to have fasteners in the form of screws or bolts in these areas here in the holes, right? So what I'm going to do here is I'm going to use a fixed constraint. You have different types of fixed, pin, frictionless, and prescribed displacement. So in this case, fixed is exactly what it sounds like. It's just going to fix that specific part of your component in space. So in this case, what I'm going to do is I'm going to fix that area, this area, and then of course the little angles that we have there going around. I'm going to hit OK, and that constraint is going to show up as little locks because they're fixed, right? So we can see those little 4 locks. That means it's good, it's doing what it's supposed to do. And then by now the only thing left for us to do is apply a load, right? So we're gonna say let's do a load. Now there's different types of loads that we can apply. In this case, let's do a single force. We can do force, pressure, moment, bearing load, remote load, hydrostatic pressure, different things like that, right? So we're just going to do force. Our target is going to be this top surface. Now here we can do things like a distributed load along the whole surface, or we can do things like a one specific load in a specific area. So what we can do there is we can modify things like a normal, delta, vectors, and then we can change the unit. So let's do that. We created this thing in inches, so we're going to switch from inches to pounds force, and then the force that we're going to apply is going to be 4,000 pounds force. 4,000 pounds. There we go. We can also flip the direction, so we can do things like that or that. In this case, I think we're all set. We have everything we need. There we go. We're going to apply that one force distributed along the entire surface. I'm going to say OK. There it is, it's showing up. Now once this is done, let's run the pre-check real quick. The study setup has all the information required. Okay, we're ready. Then all we need to do is I believe just hit results. Yes. There we go. Solved one study. Now, in this case, Fusion Autodesk works in sort of this state of credits. So everything you do on the cloud, you're supposed to have cloud credits available to you that you can use. Now, in this case, because you all have student licenses, I believe there's no limit as far as how many cloud credits you get. So just sort of keep that in mind, but also be conscious about it. Don't just go home and try 100 different studies just because you can, right? So try to be careful about that. If you're doing something that's gonna help you learn and it's gonna help you grow as a student, and then by all means go ahead and try it out and test it and give it a go, right? But just don't overdo it just because, okay? So in this case, we have we're gonna solve this one study. We're gonna save it first. So I'm gonna go into the folder for this class. There we go. And then I'm gonna call this bracket. Okay. It's gonna save it, and then it's gonna show me a status. Sometimes it takes a little bit of time, sometimes it doesn't. It just all depends on the cloud. If the study is pretty simple, it should be pretty fast. If it's very fine mesh, or if it's something a little bit more complicated, then it's probably going to take more time to solve. Right. So at this point, we're done. Now let's take a look at what's going on in here. Okay. So in this case, it's showing us a safety factor. So it's telling us that this thing is going to hold up to the constraints and forces we give it, and it's still going to maintain a 2.09 safety factor. What a safety factor is essentially the number of times that this component can actually maintain or sustain that force. Okay, so in this case, it's letting us know, hey, you can multiply the force that you're applying by 2.09, and this thing will be right at the limit of breaking. Okay, now the safety factor is very important. Remember, at this point, all we're doing is simulating a loading condition, right? But a lot of different things can happen in real life. So things like there's a defect on the material that you use to create your component, or things like there's another force that you didn't account for. So maybe there's more loading happening that you're intending for it to happen. So a safety factor is something that's critical when you're designing something. So the more important something is, the higher the safety factor, if you will. So usually industry varies somewhere from 2, 3 to things like 8, 9 safety factor, just depending on the use. Now, one other important aspect of a safety factor is the higher the safety factor is, then that directly translates to more material that's present that's not really necessary. Okay, what's happening here is you have essentially more material in the critical areas than you need for your limit, and we just have to sort of be aware of where we want our limit to be. Right now, we can also take a look at the colors. So show weakest areas of the design, and that's going to show us, that's going to bring up the areas with the highest stress concentration. So these are the areas that are most likely to fail, just given the design parameters that you gave it. Now, if we think about this, this doesn't make too much sense. Why? So it's letting me know that these areas are very likely to fail, but it's not really highlighting this edge or this top edge. And this doesn't really make too much sense, because most of the torsion is happening on this beam right here. If this is coming down, then most likely it's going to break off in this area or in this area. So always, anytime you get any results, always try to take a look at those results and try to understand if everything's making sense. Okay, so at this point I can tell you we probably did something wrong because it's not highlighting the areas that should be common for this type of failure. Okay, now at this point I'm sort of already know this because I've tried out this example before, and I know exactly what's happening. If we take a look at the side view of our component, on the top we can see how this component is actually moving away from the wall, right? But if we take a look at it from the bottom, we can see that the component is moving into the wall, where physically that shouldn't happen. That shouldn't happen in real life, right? So that's telling us that we're probably missing a constraint on this back surface to prevent this from happening, and that's why we're getting the wrong results. Okay, so before we move forward, let's go ahead and try to fix that. Okay, so what I'm going to do here is I'm going to go to study 1, I'm going to right click, and then I'm going to do clone study. Okay, so I'm just going to take a direct copy of that study number 1 and create a study number 2. Except this time what I'm going to do is I'm going to go into my load case and I'm going to go into my constraints. And if you can see, we only have one fixed constraint on the areas that should be fixed, right? But what I'm going to do now is I'm going to go to constraints again, and instead of just having a fix, I'm also going to apply a frictionless. So a frictionless sort of works like a limit. So let's use this as an example. There's a wall where this component here shouldn't go past that wall, right? So I'm going to use this frictionless constraint on this back surface. I'm going to hit OK. It's going to add that frictionless on my list. And now I'm going to go ahead and try to solve this thing again. So let's, I believe, we're going to go to results, compute it, yes, ready, solve the study. It's going to take this new change I made, it's going to solve it again, and then let's take a look at the results again and let's see what happens. So hopefully it doesn't take too much longer. There we go. I'm going to close it up. Now this seems to be making a little bit more sense. So as we can see now, there's really nothing in those locations where it previously was, and it's really showing up in those two areas where the most bending is happening, top and bottom. So this is now working pretty good. Also notice how my safety factor completely changed from 2.09 way up to 5. Okay, so we're now at a point where we can apply a load. I mean, theoretically we could apply a load 5 times the current size of the load that we gave it, and this thing will be sort of on the limit of breaking. Again, remember, you always want to have a minimum safety factor higher than 1. So just sort of keep that in mind. Okay, we're gonna close this. Now there's different views that you can get here. So not just talking about a safety factor, we can do things like show me the stress. Okay, so here it's gonna really show us the stress where it's currently happening. So the max is here, 41.11. We can also modify the units there, so we can do things like pascals, psis, or KSIs, bars, megapascals, things like that. So let's leave it at PSIs. There's roughly 6,000 PSIs of stress going on here. We can do things like displacement, where we can switch that to inches as well. The most bending or the most deflection is happening right at the edge, and that's 0.002 inches, which is really not a lot. Of course, this environment really shows you where that bending is happening, but it's not really to scale, if you will, right? And then we can have things like reaction force or strain. So those are the main ones. Again, our safety factor is pretty good. Now, the last thing I want to do is I want to comment on common things you can do to sort of minimize the stress and be able to have better results with given components. So in this case, if we take a look at where our stress concentration is, most of it is happening in this edge and on the top, right? So the top, there's really not much we can do, but to the bottom edge, there's one small change that we can do that should really help us make a big difference in this design, and that thing is running off this whole edge going on here. As long as we round that off, we should be allowing more material to take care of that stress. So a simple fillet in this edge here should allow us to bring this safety factor even higher. Okay, so just sort of keep that in mind. Now, if you remember, in this particular case, we're using steel. So the safety factor and the stress concentration and everything, all those different values are going to completely change if you change something so simple like the material. So steel is going to it's going to behave completely different to what an aluminum or what a plastic would behave as, right? So make sure you really understand what's happening there with materials. Make sure you're always using the right material. Make sure you go through the list and just sort of try to understand as much of what's happening as possible. Okay, so we're gonna leave you there. What I'll do is I will probably make something like this available on Blackboard in case you're having some issues. So I'm probably gonna make this particular model available, and then in case you have any issues or you want to sort of take a look at some of the results I got already, but by all means, I expect everyone to go through and create this component from scratch at home, and make sure you go through this process, do everything that you just saw in this video, replicate it, and then once you're good with that, then you should be ready to move on with your project number 2. Okay, so project number 2 is going to be something a little bit more involved than this, but it's still going to be a pretty simple simulation type of study. Okay, so just look forward to that. If you have any questions, please do not hesitate to email me. I'll try to answer those as soon as possible, and we'll see you once we're done with the course. So this is it for me. Okay, guys.